Hello there. In this video, I'm going to do an introduction and a bunch of review for exponential and logarithmic functions. So that'll be the first part. And as these videos progress, we're going to see how to rewrite them and eventually look at the exponential functions instead of 2 to the x power. We'll look at e to the x power. And instead of logarithms, we'll look at natural logarithms. And we'll look at the derivatives of those and do even slopes of tangent lines to curves and solving some really fun equations. So as we go through this chapter, in chapter 8 of our textbook, before we get into derivatives of that, we're going to need to do a bit of review and preview of the skills. So looking at the laws of exponents, based on what I've seen, most of my students know these quite well by the time they're doing calculus. So really quickly, if you had two bases being multiplied, those exponents are allowed to be added when you combine them. If you had a to the r all to the s power, you combine those two. When it's a product of powers, it turns into a product here, a power of powers, excuse me. If you have two numbers multiplied all to one base, you can break it apart into a to the r and b to the r. If two things are divided, they become a subtract. Multiply is an add, divide is a subtract. This rule right here and that rule right there are the same thing. The power can distribute on a product. It can also distribute on a quotient. And if you have a negative exponent, it's written in the denominator as a positive. And by definition, a to the 0 or anything to the 0 power is 1. Usually we would do some examples of that stuff, but most of my students right now seem to have a really firm grasp on that. So we're going to move to the next section and get into logarithms, which is where things tend to get just a little sketchier. Okay, so what's the point of logarithms anyway? Before where they show up and anything else, what is the point of it? And to address this, I'm going to bring up a calculator, and if you have a calculator with you, it would work quite well. So if we bring up the calculator here, it's sitting there waiting for me. So I'm going to throw in some of these x values and get my calculator to do the logarithm of that. And the log button, log, sitting over here by the number 7 in this calculator. So I want to take the logarithm of 1 million. So 1 with 6 zeros, you hit logarithm of 1 million, enter, answer comes out to 6. If we tried logarithm of 10,000, so log of 10,000, enter, comes out to 4. Logarithm of 100 is 2. Logarithm of 1. Let's try hitting the log first. Logarithm of 1 is 0. So you had here was 4, 2, this logarithm was 0. What happens with the decimals? Well, let's explore that for a second. Logarithm of 0.1 is -1. Logarithm of 0.001 is -3. And logarithm of 0.1, 2, 3, 4, and a 1 is -5. So you have -1, -3, and -5. Okay, that's what happens when you hit the logarithm of that. So it looks to me what the point of the logarithm is, or one of the functions of the logarithm, is to take numbers that are very large and change them into numbers that are much more reasonable. Changing 1 million into 6. Changing 10,000 into 4. Changing 100 into 2. 1 into 0 is not a big change. But then taking these exceedingly small numbers and also making them manageable. The difference between 6 and 5 is only 11, but the difference between 1 million and 0.00001 is a huge scale. If you were trying to graph that, good luck. But if you're trying to graph numbers that go from -5 to 6, hey, that's not a big issue, is it? So part of it is the management of numbers is one of the points of logarithms of huge or very, very tiny numbers. Where does this log come from? I'm going to add a table here, and we're going to write this in an exponential form. So let's just write exponents. 1 million is really 10 to the 6th power. 10,000 is 10 to the 4th power. 100 is 10 squared. 1 is 10 to the 0. 0.1 is 10 to the -1. 0.001 is 10 to the -3. And all of those zeros is 10 to the -5. I think at this point there's a glaring pattern as to what the logarithm is doing. The logarithm is returning the power of the base, the exponent. Now, logarithm is implied that it's base 10. So for an log on your calculator, that's assuming base 10 if there's no other base written in. And so you get the power back. Now, it won't be exactly true if you used 20,000, because 20,000 is 2 times 10 to the 4. The answer is not going to be 4. If we try the logarithm of 20,000, log of 20000, hit enter, you get a number just bigger than 4, 4.301 or something. So it's on its way up to the next power. It's on its way up to the 5, or 10 to the 5th. So it is getting closer to 5. So it's going to be slightly larger. This is where we need the calculator. If you just had 10 to the 4, you don't need a calculator. You can predict that it's 4. If it was 10 to the 2, you can predict the 2. If it's a different number, that's where you need the calculator to work it out. But I don't want to try to go too far off the topic here, but the idea of a logarithm is, the point of it is to take large or small numbers and make them manageable. Okay, so where do logarithms show up? Well, tons and tons of places. A lot of biological phenomenon would be nonlinear, and if they're nonlinear, we can use logarithmic functions to represent them oftentimes. So the growth of populations tends to be logarithmic. The relationship between different parts or aspects of an organism, so the allometric relationships, so many things are logarithmic there. Number of species given in an area, that's like population itself, species to area relationships, radioactive decay, carbon dating, earthquakes are one with the Richter scale, pressure amplitudes in terms of the sounds you hear and the decibel levels, those are logarithmic scales. There are many, many, many others. So it turns out exponentials, logarithmics, and these allometric functions are useful to understand, are useful or use logarithms when we want to understand them. Okay, so if we looked at population growth, if it's growing geometrically, it would go from 1, then it doubles to 2, doubles to 4, doubles to 8, then 16, 32, 64. The numbers are going to blow up quickly, getting up to 128, 256, 512. If it keeps doubling, they start off where it's not that big of a growth. But boys, once you get moving, it gets huge. Looking at the y values for that, you would see that it climbs not very much at first, and then starts climbing faster and faster and faster, really increasing quickly. But if you were to apply a logarithm to these, and not necessarily log to base 10, but in general, if you apply the logarithm to these, the numbers change from numbers of cells that are climbing very quickly to the log of those numbers, 0, 1, 2, 3, 4, and all of a sudden you get a pattern that looks like a straight line. So you've changed an exponential, or you've changed a nonlinear function into a linear function. So, and that is something you can deal and predict much better. You can figure out rise over run on here. you can read values much more accurately than you could read predicting y values off of this curve when you're sketching in how curvy it is in between dots. So it's also a function in terms of graphing that will sometimes make not just the function, but the graphs of the functions so much better. Okay, so another point of logarithms. If we looked at the wound healing rate, so if the area of a wound and how much smaller it gets as it heals, for being 107 square centimeters, and as time goes on, the size of the wound is decreasing. So the question is, if you were to plot that and take a look at it, the regular plot would show, you would attempt this green straight line, but if you look at the scatter plot and look at the points, it certainly looks like it is a curving function. It looks like it is an exponential decay. And if it's an exponentially decaying question, you could take a logarithm of that, and if you take a logarithm, they line up to make a straight point or straight line. So really useful function, as you can see. These aren't things that we are going to do. I'm just selling how awesome these logarithms can really be. Okay, so let's get to the nitty-gritty where things tend to fall apart here. So when we write a logarithm, you could write it in a generic, this would be a generic exponential equation. Let's say b to the y equals x. And then we could write log b x equals y. What you would say here, one is an exponential function, one's a logarithm. They are just inverses of each other. One is the opposite of the other, just like a square and a square root undo each other. If you had x squared equals 9 and you want to solve for x, that is not a barrier for you anymore because you know how to undo a square, and that is to take a square root. And when you do that, you get plus or minus 3. It's intuitive for you that you know how to undo a square. It's the square root. Why? Because they are inverse functions to each other. Well, so is it true for exponential equations and logarithmic equations. If you've got an exponential equation and you want to undo it, you're going to just throw logs in there. And I know students look at it and they say, why am I just throwing logs in there? But nobody asks, why did I just throw square roots in there? You threw square roots in because you need to solve the equation. Same answer for exponentials and logarithms. If you've got some type of exponential function and you want to get rid of that, you've got to take a logarithm of some type to undo this exponent, right? That's how you have to do it. They're just linked together. So exponents and logarithms are inverses of each other. I'll get rid of this square root square stuff. Okay, so how would we say this in words? Well, when you see log b x equals y, you would say log to base b is the base, log to base b of x, that's what you're taking the log of, equals means is y. Okay, so this is the base, right? And this is what it's equal to, and that is what you're taking, the x is what you're taking the log of. Okay, in other words, so another way to say it, log to base b of x, that answer is the exponent to which the base b must be raised to give x. So if you had, well, we'll see other examples after. I won't put it in here. So my examples may be worse than what I'm going to give later. All right, so let's label what in these two functions underneath here. What are the bases and what are the exponents? Okay, so we have a base and we have an exponent. In this exponential equation, the base is b and the exponent is y. And look what happens when you write it in exponential form. The base is still b, and now the exponent is the y that's out here. Okay, so when you want to change this function into that function, this is how they move around. The base goes here, the equals is the exponent, and the x that you're taking the logarithm of is your answer. All right, we're going to play a lot more with that and with these laws of logarithms. First, we'll just look at writing some of these in exponential form and in logarithmic form. Okay, so if we wanted to express something in an exponential form, what we're trying to do, if you're thinking of this, log to base b of x equals y, and that is b to the y equals x when you write it. Those two things are synonymous to each other. So if we follow that pattern and work our way through, one's logarithm and one's exponential. So this is logarithmic form, and we want to write it in an exponential form. So the base is 2. So 2, this is the exponent to the -1 equals 1/2. Well, that's pretty simple. You knew 2 to the -1 is equal to 1/2. So this is your answer. You've written that expression, the logarithmic expression. We have converted to an exponential form. So let's work it backwards. Let's take this exponential form and write it as a logarithm. So we write log. What is our base? The base is 2. So log to base 2 of what thing is 1/8. And what does it equal? It equals the exponent -3. All right, so can we use these rewriting powers to actually solve questions? Well, for some of them we can, because if we just rewrite this in exponential form and then try and solve for x, let's see if we can figure out what happens. So writing this, the base 2 to the power of 3 is equal to 25 subtract x. So 2 is my base, 3 is the exponent, and what's in brackets goes out there. So 2 to the 3 equals 25. I believe you can solve that equation. 8 equals 25 subtract x. Simple rearranging. 25 take away 8. Looks like you get 17. Right? Trying to write this as a logarithm instead, you could take this one that's given and try and write it. This would be log to base 3 of 7 equals x plus 2. And now getting x by itself, you would take the 2 over and subtract, and you get log to base 3 of 7, subtract 2 equals x, and you'd have to work that out, which is beyond what we would do right now, but at least you could write it that way as what its expression is equal to. All right, so we've gone over writing exponentials, we've gone over writing the forms, and we've done a little bit of the logarithms. What I'm going to ask you to do at this point is to try some questions, and the questions we're going to get you to try, well, is questions 1, 2, and number 3 from page 352 to 353. And I'm going to turn the video off.